Hi everyone, and welcome to Unit 1 Video 3. This is also the third lecture of Chapter 6, and in this lecture we're going to focus on electron configurations and we're going to look at orbital diagrams. And so if you need extra review or extra practice, or you want to see some practice problems, go ahead and read section 6.8 and 6.9 in the book. That's what actually covers the electron configurations and orbital diagrams. So before we talk about electron configurations, I just want to continue our discussion with quantum numbers. So the Pauli exclusion principle states that no two electrons in the same atom can have exactly the same energy. So what that means is no two electrons in the same atom can have identical sets of quantum numbers. This is why we focus on m sub s. So now we're going to actually focus on that most specific fourth quantum number, the m sub s, which tells us the spin. So because no two electrons can have the same set of quantum numbers, this is why we have the two values of n. We have +1/2 for m and -1/2. So the Pauli exclusion principle allows us to reference a specific electron in an atom by giving their set of 4 quantum numbers, and therefore we can define the region of space in which the electron is most likely to be found. So from now on, we can actually use all 4 quantum numbers to describe one specific electron. So by understanding the relative energies of the orbitals and by understanding the Pauli exclusion principle, we can now consider the arrangement of electrons in an atom. So the electron configuration shows the distribution of all of the electrons in an atom. The most stable organization, the most stable electron configuration is called the ground state. This is where the electrons want to be whenever possible. They want to be in the ground state because that is the lowest energy. So when we're focusing on the electron configuration, first we have this large number. This large number denotes the energy level. So this is the principal quantum number. Okay, n is the principal quantum number. The next letter that we have, in this case it's a p, denotes the type of orbital. So this tells us what sublevel we're in, which is based on the value of L. Right? L tells you the sublevel that you're in. And then finally, we have this superscript. So in this case, it's a 5. And the superscript tells us the number of electrons in the orbitals. So in this case, in the p sublevel, we have 5 electrons. So this is the overall electron configuration. So as we go through electron configurations, it's important to know how we fill the orbitals. So we fill the orbitals in increasing order of energy. Now because of the Pauli exclusion principle, we have to make sure that we fill the orbitals in order of increasing energy. The reason the Pauli exclusion principle is important is because it tells us that at most there can be 2 electrons in a single orbital. Now if there were no restrictions on quantum numbers at all of the electrons would want to go into that 1s orbital because that's the lowest energy. However, that's not the case, and so we have to go from lowest energy, which is 1s, to highest energy, which is really based on the atom that we're working with. So the periodic table is a great way to help you with electron configurations because different blocks on the periodic table, which in this case are shaded in different colors, correspond to the different types of orbitals, the different sublevels. So if we look at groups 1 and 2, okay, that's the s block. So this blue is the s block. Then we can actually work our way over. So think about it reading a book, right? Think like you're reading the page in a book. You start on the left side, you work your way right, and then you go down to the next line. That's exactly what we do using the periodic table. So we start up here at the 1s. Okay, so we start at the 1s, we work our way over, then we come down to the 2s. So then we fill the 2s, work our way over, then the 2p, come down to the 3s, then the 3p, then we come to the 4s. If you remember from the energy level diagram that we did in class, the 4s is actually lower in energy than the 3d. So we fill the 4s first, then the 3d, then we go to 4p. So this blue represents the s, the pink is the p, the orange is the d, and then the tan are the f block elements. So this is how we go through and how we fill energy levels based on the periodic table. So this diagram that you have on the slide now is simply a picture to help you remember the order of filling the sublevels. So if you take a look on here, you start with 1s on the bottom, and then what you do is you just write each of the sublevels that are in each energy level. So we come up to 2 and we have 2s and 2p, then we come up and we have 3s, 3p, 3d, and so on. And then what we can do is we can actually just draw arrows. So we start down here and say first we fill the 1s, then we fill the 2s, then we fill 2p, then 3s, then 3p, then 4s, and so on. So this is just one diagram to help you remember the energy level and the order of filling each of the orbitals when you're writing electron configurations. So this is another diagram that I prefer over the one on the previous slide, but sometimes people learn differently and just the organization of one diagram over the other helps certain people. So I wanted to show you both just so you could use the one that makes the most sense to you. But I like this one because it's easy for me to actually just write out the energy levels with the specific sublevel in order first. So, start with 1s up at the top. So start with 1s here, and then actually just come down and say 2s, and we can have 2p. Then come down and write 3s, 3p, 3d. Then come down, write 4s, 4p, 4d, so on. And then what we could actually do if we wanted is we could actually continue the 5th energy level, and then we could continue the 6th energy level, and so on. But that's just, if we wanted to continue. Now, when we go through this, I like this because we can, again, just follow the straight arrows as we go through. So we start with 1s, come back up, come back down. So we're just going diagonally. So we start by filling the 1s, then we fill the 2s, then the 2p, then the 3s, then 3p, then 4s, 3d, 4p, so on. Now again, if you look at that periodic table that I gave you that's also in your notes, this is actually the exact same as if you read it left to right. So if you read the periodic table left to right, it would go in this exact same order, which is lowest energy to highest energy. So just a reminder with energy levels, when we're focusing on multi-electron atoms, which is every atom except for hydrogen, the energy levels are not degenerate. The energy levels are all different. So 1s has the least energy down here at the bottom, then 2s, then 2p, and so on. So when we draw orbital diagrams, it's important to actually draw everything in the specific order of energy to make sure that you represent that these energy levels are not degenerate. So now that we looked at electron configurations and how to represent that, we're going to look at orbital diagrams, which actually help you write the electron configuration, especially if you don't really remember it. So if we look at these orbital diagrams, they are represented using these boxes. So each box represents one orbital. So 1s has one box because it has one orbital. And then within the box you have half arrows. And these half arrows represent the electrons. And then the direction of the arrow represents the relative spin. So if the half arrow points up, that is positive spin, that's plus 1/2. If the half arrow points down, that's minus 1/2. So if you look in lithium's 1s orbital, we have the plus 1/2 and the minus 1/2 electron within that orbital. So as we look at orbital diagrams, it's important to know Hunds Rule. And Hunds Rule states that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So Hunds Rule is based on the fact that electrons repel one another. Electrons are negative. When you have two negatives next to each other, they repel. So by occupying different orbitals, which is what Hunds Rule states, the electrons are as far apart as possible to minimize the repulsion, and that's the lowest energy. So Hunds Rule means that for a set of orbitals in the same sublevel, so for instance the 2p, there must be one electron in each orbital before pairing the electrons, and the electrons have the same spin as much as possible. So when electrons have the same spin, kind of like these electrons in the 2p, when they have the same spin, they are said to have parallel spins. So again, that's to maximize, or essentially to minimize, energy, right? So we want energy to be the lowest possible. So by first singly occupying orbitals, and then by having them all have the same spin, that's minimizing repulsions, which is minimizing energy. So Hunds Rule is very important as we look at orbital diagrams. If you can't remember Hunds Rule, just remember Hun didn't want to share a room with a sibling, right? They all should be in separate orbitals before pairing up. So now that we've talked about orbital diagrams and we talked about electron configurations and the periodic table, it's important that you guys know one shortcut to help you as you write electron configurations, because electron configurations can become very long if you're using the longhand form. So there are shorthand electron configurations. So they could be called shorthand, they could be called condensed, or they could be called noble gas configurations. So the first thing that's important is elements in the same group have the same number of valence electrons. So valence electrons are based on the group that atoms are in. So group 1, for instance, has 1 valence electron. If you notice, all of the configurations are similar, right? They all have the noble gas and then blank S1. So that is important to know. You have to be able to see patterns within the same groups on the periodic table. If you see table 6.4 in the book, that kind of shows you what I mean by looking at the patterns. I would highly recommend that you look at table 6.4 in your book. So coming back to condensed configurations, the filled inner shell are called the core electrons. So anything that is not valence is core. So what we can do is we can write a shortened version using brackets around the noble gas and listing only valence electrons. So if you notice for lithium, okay, we have helium in brackets because that's the noble gas from before, and then 2s1. If we come down to rubidium, krypton is the noble gas before, so having krypton here in brackets represents the entire electron configuration of krypton, followed by 5s1 because that's the 1 valence electron. So you will be able to use noble gas configurations, but it's also important that you know how to do the longhand. So there are some irregularities when we don't have enough electrons to completely fill an orbital, but when we do have enough to half fill different sublevels. So some anomalies we have on the periodic table we're going to take a look at, and it is important for you to know these irregularities. So one example of this irregularity is the electron configuration for chromium. So if we look at chromium on the periodic table, transition metal, atomic number 24, there are 24 electrons. Okay, so there are 24 electrons. If we look, we have the noble gas, which is argon. Okay, and then we're going to fill what's next. So we are in 1, 2, 3, 4. So we're going to put argon in brackets, and then 4s, 1, 2, 3d, 1, 2, 3, 4. So we would expect it to be argon, 4s2, 3d, 4. But because we have the 4s completely filled and the 3d with 4 electrons, we can actually move one of the electrons from the 4s into the 3d to half fill both sublevels. This actually makes it much more stable because of 2 half-filled shells rather than one lower energy filled shell and then having the 4 electrons in the 3d. So this is one of the irregularities. So the reason that this occurs is because the 4s and the 3d orbitals are very close in energy. So the 4s is only slightly lower in energy than the 3d. When we have these half-filled sublevels, they have this extra level of stability compared to other electron configurations. And so because of this, the ground state isn't what we predicted. So other examples would be molybdenum, okay, Mo, right underneath chromium. We also would have copper and silver as two other irregularities that don't follow our normal expected ground state. And you can actually see that right on this periodic table. So you have this periodic table in your book. This would be very helpful just to look through to focus on any other electron configurations that might not make sense. So these irregularities also apply to the F block. And the lanthanide and actinide series are different in and of itself because last year, it kind of depends on how you learn it, but the lanthanum series, which comes after barium, and the actinide series, which comes after radium, some resources have these starting as D1. Others have it starting as F1. So it's important that we kind of look through this. We're not going to focus as much on these rare earth elements just because they are a little bit different. But please read page 240 and 245 on these F block series just to help you get a little bit more acquainted with these elements and why they're a little bit different. So what I want you to do is actually pause the video and I want you to try example A and example B. So example A says to write the electron configuration for phosphorus, which has the atomic number 15. Now I want you to write the longhand and the shorthand just to get used to that. And then I want you to draw the orbital diagram. Once you draw the orbital diagram, then I want to know how many unpaired electrons does a phosphorus atom possess. So do both of these examples, pause the video, and then come back and we can go through these examples together. So when you're writing the electron configuration for phosphorus, it's important first to know how many electrons we have. So phosphorus in this example, I already tell you, has the atomic number 15. So there are 15 electrons. So what we're going to do is we're just going to start in the top corner of the periodic table and we're just going to work our way across. So we're going to start with 1s, we fill that completely, we come down. 2s, we fill that completely. Then we go across to the 2p, which we also fill completely. Okay, then we come down to 3s, haven't hit phosphorus yet. Now we have to count in how many elements in phosphorus is in that 3p block. So if we count in, okay, we have 1, 2, 3 elements in. So you should have your periodic table as you go through any electron configurations, because without your periodic table, you might be kind of lost. So when you look again at your periodic table, okay, when you look at that periodic table, you count in how many atoms in phosphorus is. It's 3, therefore it is 3p3. Now when we look at the noble gas notation, okay, it's important for us to look at this as well. What we do is we look for the noble gas right before. So we're going to put the last stable atom in brackets. So if we find phosphorus, look back at the previous noble gas, okay, and that is neon. So we're going to put neon in parentheses, and then we're just going to complete the configuration again. So it's neon, 3s2, 3p3. So we have both the longhand, which is this first. Okay, so here's the longhand, here's the shorthand. Now we'll go through the orbital diagram. So it's important as we go through the orbital diagram, I'm just going to use lines. Usually we use boxes, but I don't have as much space. So we start with 1s at the bottom, okay, then 2s, then 2p, then 3s, then 3p. So now we're going to fill this. Okay? Hunds Rule says that we start putting them in, put the electrons in on their own first. Okay, so 1, but we have to fill that orbital before we can move on to, or that sublevel before we can move on to the next. So we have 1s2, 2s2. Now when I'm in the 2p, I'm going to put an electron in each orbital first, then I'm going to come back and fill it up. It's good to get in the habit of doing it that way. Then 3s, and then 1, 2, 3. So we have 1s2, okay, 2s2, 2p6, 3s2, 3p3. So this says how many unpaired electrons does a phosphorus atom possess? Well, the answer is going to be 3. Okay, all of the electrons in that 3p are not paired. Those are unpaired electrons. So this was an example. Hopefully it helped you as you went through. If you have other questions, please ask them. If not, then we'll just go through some practice in class to really solidify these electron configurations.